Welcome to those on Zoom. Let's talk about antiderivatives. So the real story with antiderivatives is, I should get my papers out here, is basically, if you know how to differentiate a function, then you know how to anti-differentiate the derivative of that function by just going back to where you started. And we did a couple examples last time. Where's my, where you at? I lost a piece of paper. Just 1 second. Did I not take you with me? It'd be real unfortunate. That's not that unfortunate. Oh, there you go. I found it. Okay, good. So, yeah. Examples here. It's too much, not enough room. There's never enough room up here. Okay. So just some examples. If I wanted to, let's go sideways. So if I want to find the antiderivative of 1/4 x to the 7th plus 3, I don't know, secant squared of x minus 7e to the x plus 2. These are all things I recognize as the derivative of something else. X to the 7th is the derivative of x to the 8th over 8. So I know the antiderivative here is going to be 1/4 times x to the 8th over 8. The great thing about constant multiples is, just like with differentiation, with anti-differentiation, they still just hang out. So if you've got something multiplied by a constant, that constant multiple is just going to stick around. Same deal here. This 3 that's a multiple of this function is just going to stick around. And we do know a function whose derivative is secant squared. It's good old tangent of x. We also know a function whose derivative is e to the x. I just said it. It's e to the x. So the antiderivative of 7e to the x is 7e to the x. And then the antiderivative of 2 is 2x. And be careful, that's not a backward 6. That's a dx. So that just tells us what variable we're anti-differentiating with respect to. So then at the very end, a good old plus c. Okay. Let's see. Anything else? Oh yeah, sure. So sorry, I'm getting weird messages. All right. A couple things to be aware of. Sometimes things are not going to be just this easy. So it's really nice if you've just got all these single pieces that each anti-differentiate straightforwardly. That's not always going to be the case. For instance, you might have some stuff multiplied together, like something not too bad. X cubed plus 2 times 2x plus x to the negative first. So if I want to anti-differentiate this, I can't just anti-differentiate each factor and multiply it together. Kind of like how the product rule works for derivatives, right? You can't just differentiate a product and like take the two derivatives and multiply them together. The same thing is true here. You can't anti-differentiate a product just by saying it's the antiderivative of this times it, right? We have to just multiply it out first. So I'm going to rewrite this as still the antiderivative of, and then I'm just going to FOIL this thing out. So I've got x cubed times 2x, which is going to be 2x to the 4th. And x cubed times x to the negative first is going to be x squared. And then 2 times 2x is going to be 4x. And then 2 times x to the negative first is going to be 2x to the negative first. Okay, and then each of these we can just use the power rule for. Well, it's kind of a lie, but we'll see in a second. We can't. So for 2x to the 4th, we're going to get 2x to the 5th over 5. And for x squared, we're going to get x cubed over 3. And for 4x, we're going to get 4x squared over 2. And for 2x to the negative first, we're not going to get 2x to the 0 divided by 0. You can't divide by 0. So it's really important that when you see this, I mean, really, to be honest, when I see this, I'm always thinking of this as 2 times 1 over x. I'm always thinking of x to the negative first as 1 over x, because it's just an easier way for me to be like, oh yeah, the derivative of the natural log of x is 1 over x. I never say the derivative of the natural log of x is x to the negative first, even though they're the same thing. It's just not the way we usually say it in our heads. So, oh, the antiderivative of x to the negative first is going to be, well, the 2 hangs out, and then we get a natural log of not just x, but the absolute value of x. And again, I promise you we will get to why that is what it is in a little bit here. We're not quite there yet. Plus C. So sometimes a lot of the time, actually, before you anti-differentiate a thing, it's really going to be worth your while to simplify it first, meaning to multiply it out, or maybe like in this next one, to divide a bunch of things. So like, for example, if I wanted to find the antiderivative of 6x to the 5th plus 5x cubed plus 1, all divided by 2x squared, there is no anti-quotient rule. We just have to simplify this thing. So we're going to divide each thing by 2x squared. And that's kind of a common tactic when you have a fraction or a quotient where the denominator is a single term, right? I'm thinking of 2x squared as a single term, it's not like 2x squared plus something else. So here we're just going to rewrite this as the antiderivative of 6x to the 5th divided by 2x squared plus 5x cubed divided by 2x squared plus 1 divided by 2x squared. Now what? Now what indeed? Sorry, I know someone said something, but I didn't hear you. Well, yes, but there's something we want to do first. Because I don't know off the top of my head what the integral of 6x to the 5th over 2x squared is. Well, I need to do something first. Simplify. So if we simplify, this is going to become 6 divided by 2 is 3. X to the 5th divided by x squared is x cubed. Same deal here. 5 over 2, I'm just going to leave as 5 over 2, although you could write 2.5 if you like a decimal. I prefer a fraction. And then x cubed over x squared is just x. And here I would rewrite this as 1/2 times x to the negative second. So they're all x to a power and they're not in the denominator, right? We want them all out of the denominator if they were in the denominator. And now we can just anti-differentiate and get 3x to the 4th over 4 plus 5/2 times x squared over 2 plus 1/2 times x to the negative 3rd over negative 3. And we should simplify that. We could certainly write this as 3, and I don't care if I write 3/4 times x to the 4th or 3x to the 4th over 4. It's kind of the same either way. It just is a matter of personal preference. I'm going to write 3/4 times x to the 4th. 5/2 times 1/2 is 5/4 x squared. And then here I'm going to get a negative 1/6 x to the negative 3rd. That's how I would probably choose to write this. Did I make a mistake? I did, but you guys let me get away with it. What did I do? Right. So this is not the right power here. I totally biffed it right there. I should be adding 1 to the power, which should give me x to the what? Right. So this is not correct. This is not correct. What I should actually have is 3x to the 4th over 4 plus 5/2 x squared over 2 plus 1/2 x to the negative 1 over negative 1. And then if we simplify, we get 3/4 x to the 4th plus 5/4 x squared minus 1/2 x to the minus 1 plus c. See about that. Sorry, where'd you go? Always too many papers here, not enough room.
We did one to write on homework.
Sure. Is there a particular homework problem you have in mind?
Yeah, I think it was number 9.
Okay, sure. Yeah, I mean, yeah, I would say these are fairly similar to that, but yes, we can look at something a little bit dicier like that. So let's say, see, I feel like I would want to make this problem harder. So I'm going to make it like number 9, but I'm going to make it a little more interesting first. Let's say we have something like this. Let's say we have, let me see, let me do some quick mental math here. Well, let's say I've got, 8x to the 3rd plus 7x squared plus 4x to the 10.7 minus 4x to the, it's going to be terrible here. Sure. 13 thirds plus 3x to the, sorry, I gotta bring it up here, 17 halves. Oh yeah, I know, it's terrible, right? All over x to the 5th. This is like problem 9 in your homework, except I'm giving you an additional beginning step here. So in this problem, before we can do anything else, we need to divide each thing by x to the 5th. So let's do that, which really just means each of these things that have x to a power, the power of x is going to decrease by 5. So you could really, I mean, you could write a lot of exposition if you wanted to. You could write this as the integral of 8 times x to the 3 minus 5 plus 7 times x to the 2 minus 5 plus 4 times x to the 10.7 minus 5 minus 4 times x to the 13 thirds minus 5 plus 3 times x to the 17 halves minus 5. So fun. And then we actually do the subtraction. So you get 8 times x to the negative second plus 7 times x to the negative third plus 4 times x to the 10.7 minus 5 is 5.7. And then, ooh, fractions, okay. 13 thirds, so 13 thirds minus 5 is 13 thirds minus 15 thirds, which is going to give me a negative 2/3 power. And 17 halves minus 10 halves is going to give me a positive 7 halves power. So now we are ready to actually do our anti-differentiation. But really, we did need to take a couple steps here to really write it so that everything was a constant times x to a power. All right. Now we just throw our rule at it. And remember, we're adding 1 to the power. So negative powers, like I forgot last time, right? Negative powers should get less negative. Positive powers should get more positive. So here I'm going to get 8x to the negative first divided by negative 1. Here I'm going to get 7x to the negative 2 divided by negative 2. Here I'm going to get 4x to the 6.7 divided by 6.7. Don't love that. Minus 4 times x to the, okay, adding 1 to the power here is going to be negative 2/3 plus 3/3, which is positive 1/3 divided by 1/3. And here adding 1 to the power is going to be 7 halves plus 2 halves is 9 halves divided by 9 halves. Now, we should not leave it like this. 1, I don't want to type all these gross fractions into WebWork if I don't have to. And 2, I don't have to. So I can definitely simplify a few of these things. I'm going to write this as negative 8 times x to the negative 1 minus 7 halves x to the negative second. This next one, you are kind of stuck with a fraction. There's nothing you can really do with 4 divided by 6.7. I mean, I guess you could throw it into a calculator and see if it came out nicely, but I doubt it does. So I would just leave this as 4 over 6.7 times x to the 6.7. These last two things we really should simplify. So whenever your power is fractional and you end up dividing by that fraction, instead of dividing by the fraction, you just want to multiply by the reciprocal. So instead of having 4 divided by 1/3, we're going to have 4 times 3, which is 12. Question.
Is that supposed to be 6 or 2?
Where?
The second x. 7 halves.
Here? Sorry.
Yeah.
Oh, here?
No, on the
Very bottom line.
very bottom equation.
Okay.
that You're working out now, 7 half x to the negative.
Oh yeah, that should be a 2. I don't know why my 2 game turned into a 6. Looking at things wrong. I think I was probably looking at the 6 over here and started. Sometimes your brain starts thinking about the next number you're going to write down, and your hand writes down the next number you're going to write down before it's supposed to. Sorry, thank you. So then instead of 4 divided by 1/3, we have 4 times 1 times 3, which is 12. X to the 1/3. And the same deal here. Instead of 3 divided by 9 halves, we have 3 times 2 ninths, which is going to be 6 ninths, which reduces to 2/3. And that's probably, unfortunately, the easiest way to input it into WebWork. It's gross though, right? I mean, although to be perfectly honest, if you saw a question like this on the test, you would be fairly happy because this is a really, aside from the simplification, which isn't that bad, this is a relatively straightforward problem. They're just giving you powers of x and you just apply the anti-power rule. Let's look at a slightly different application of this. So let's say we had something like the following. Sorry, I'll leave it there for a second. Let's say we had something like, what do I got? Sure. Find f of x if f prime of x is equal to 6 times the cube root of x plus 7, and I don't want to make my life too hellacious here. Sure. F of 8 is equal to -6. So why did they give us extra information? Well, let's first just see what they're really asking us to do here. So they gave us the derivative and they asked us to find the function. That means they're asking us to find the antiderivative of f prime. Right? If they give you a derivative and they want you to go back to the function, it's just an antidifferentiation. So step one, well, this is I might have picked numbers that are going to turn out ugly. That's totally fine. We're going to find f of x by doing the antiderivative of f prime of x. That is, again, say this 1,000 times. That is the very nature of what's going on. You take the derivative of a function to get the derivative. You take the antiderivative of the derivative to get back to the function. So we're going to anti-differentiate. Let's rewrite this as 6 times x to the 1/3 plus 7. Okay. So now we're going to do it. In fact, you all do it. Find the antiderivative. Do it on Zoom as well. Find your antiderivative. I organize the papers here. Yeah, we can look at that too. That's good. Sure. So what I want you all to get in the habit of doing is when you get x to a fractional power, immediately saying dividing by 4/3 is the same as multiplying by what? That's right. So I'm going to go straight to, I usually write x to the 4/3 and I'm like, oh, I'm not going to divide by 4/3. I'm going to multiply by 3/4. It's going to happen a lot. So that's why I would encourage you to get used to that. So simplifying this just a tiny bit, 6 times 3/4 is going to be 9/2. So our function is 9/2 x to the 4/3 plus 7x plus c. And what I would say is that this is the general solution. Meaning, if I just said find any old antiderivative, this is what you'd be looking for. However, they have given us more information. They gave us what's typically referred to as an initial condition. So if you see find an antiderivative and they also told you f of something equals something, that typically means what you should really read when you see this is, this means we have to solve for the constant c. So whenever you see an initial condition like that, you should be like, oh, I'm going to find an antiderivative. There's going to be a plus c, and then I'm going to have to plug that in to actually figure out what the c value is. Now, I've picked not very nice numbers because I just made this up. It's probably not going to turn out very nice. We're still going to find it. So what we're going to do is we're going to take our function, and then we're going to plug in that f of 8 equals -6. So I'm going to plug in 8 for x, and f of 8 equals -6. Okay, so f of x is going to be f of 8, which is going to be -6. And that's going to equal 9/2 times 8⁴ plus 7 times, I could have just picked 1, but I had to be fancy about it. Oh well. Not impossible, just not fun. So let's see. So we have 8⁴, which is 16, right? Because it's the cube root of 8, which is 2, and 2⁴ is 16. That's going to be 9/2 times 16. 7 times 8 is 56 plus c. So then I have numbers kind of big. 9 times 8 is 72. So I have -6 minus 72 minus 56 equal to c. And that's something. It's what? I don't know. -128, -134, I think. Oh. See, that's what happens. You write a number and you think of another number while you're writing a number, and you just like maybe it's because I'm getting older. I think that might be it. It's because my brain doesn't always want to talk to my hands the right way. Okay, here's what I should say. We're not done. We're almost done. But once you find the c value, you then have to go back and write down what the actual particular solution is. So there's your general solution, and our particular solution is just plug in c. But we actually need to write that f of x equal to 9/2 x⁴ plus 7x plus, minus, but I'll just write plus -134. That is our actual particular solution. So whenever you're given this extra initial condition kind of piece of information, that means we have to go do more work and find out what that constant value c is. Let's look at 1 or 2 more. So the homework that I think you all have due today doesn't look too terrible. I think that's this. I mean, no, they're all pretty much just using the power rule. Yeah. Yes. So I will point out, I will walk through for the first time because I didn't really do a good job of explaining it. So when you have 8⁴, or basically any number to a fractional power, we could have just left it like that, right? We could have totally written our answer, although it would have been ugly, as c equal to -6 minus 9/2 times 8⁴ minus 56. But that would have been awful, right? I don't want to do that. So 8⁴, we can write that as 8⁻⁴ to the 4th. And what's the cube root of 8? And what's 2⁴? 16. So that's what's happening there. I will mention you can do it in the other order, meaning you could do 8⁴ first and then the cube root of that. I don't recommend it, but you can. It's like, so 8⁴ is 4096. And then the cube root of 4096 is, well, I'm pretty sure it's 16 because it's the same either way. But yeah, you don't want to do the power part first and the root part second. You want to do the root part first and the power part second, if you have something like that. And the only reason I know what 8⁴ is because of that dumb 20. Remember that game, the people the phone game that was popular, the 2048 game, like 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. I don't think I ever got to the next one, but right, those numbers are all powers of 2. So if you're looking for 8⁴, which is really 2⁻², that's what it is. Anyway, other questions? Yeah.
What's the difference between an integral and an antiderivative?
Fair enough. I feel like I put that off long enough. So here's the idea. And so this is moving a little ahead of where we are, but it's worth mentioning now because we're going to definitely come back around to it eventually. So the reason we use this integral symbol really is because, so I would say you probably don't need to take notes here. Like this isn't going to come up for a little while, and I think you'd be better served by listening. Also, I will post the notes later later today, probably like 4 or 5 o'clock-ish. So if you want to go back and look at them later, you're fine. So you don't need to write this down. I think you'll be better served by not doing it. So the reason we talk about integrals mostly is we're trying to find the area under a curve. So under, for example, f of x, where x is between some constants. Usually we say a and b. So graphically, it looks like this. We've got some function, f of x, and between a and b, I want to find the area. So there's the area. Okay. So the thing about this is we use the integral notation to represent this. So the area under the curve of f of x and above the x-axis between a and b is equal to what's called the definite integral. It is the integral from a to b of the function with respect to x. All this means is the area under f of x between a and b, which is all we've written down here, right? That area between a and b under f of x. Okay, so here's where things really come into play. The way we're going to calculate this, and this is what's part of the fundamental theorem of calculus. The way you, or I should say, one way you can calculate the area under a curve. Well, one way you can calculate this is by like looking at the thing and being like, is it a shape I know? For example, I'm gonna get, I'm really, okay, how much time have we got? I can give this like 5 minutes. All right, so here's an example. Let's say my curve was a straight line, like y equals 2x plus 1. And I want to find the area under the curve from 0 to 4. So I want to find this area here. I could use an integral, like the way you're going to eventually, but I could also recognize that's a triangle and a rectangle. And I know how to find the area of a triangle and a rectangle. So this, if I plug in 4, 2 times 4 plus 1 is 9. And if I break this up right here, I know this has a height of 1. So this rectangle has an area of 4 by 1. And this triangle has an area, well, it's 4 wide, it's 8 high, it's 1/2 times the base times the height, which is going to be 16, I think. Yeah. So in total, this red area is 20. Okay, that's one way we could find the area because it's a shape we know. But what we're going to see is that the fundamental theorem of calculus says you can find the area under a curve, in this case, from 0 to 4, always the leftmost value on the bottom, the rightmost value on the top, of our function by finding any antiderivative of that function. So what's the antiderivative of 2x?
X squared.
And what's the antiderivative at 1?
X.
And then we don't need a plus c, although you could have one. You could have plus 6, for example. So I'll put on, let me do a plus 3 here. I hope that my numbers come out. Yeah. So I really just want to point out, we don't need this. Not needed. Here's why. What you do after you find the antiderivative is then you evaluate your antiderivative at the top value. So that's going to be 4 squared plus 4 plus 3 minus your antiderivative evaluated at the bottom value, which is 0 squared plus 0 plus 3. And notice two things. One, whatever that constant is there is always going to cancel out with itself. So you don't need it. So that's why people say when you have a definite integral, or you have limits of integration, you don't need a plus c. And the other thing I want to point out is this is equal to 20. 16 plus 6 minus 0 plus 0 is 20, which is the same. Okay, so I know it's a very, very long answer to your question, but here's the deal. The fundamental theorem of calculus says, or I should say one of the parts of the fundamental theorem of calculus says, that you can find the area under a curve, which we usually use this symbol for, by finding any antiderivative of the function, and then plugging in the endpoints and subtracting. And therefore, because of this, because there's this inextricable link between finding area under a curve and using the antiderivative, we essentially say, well, we're going to say that the integral and the antiderivative are essentially the same thing. So when we find a definite integral, we use the antiderivative to help us calculate that value. And then when we find the integral, aka the indefinite integral, meaning you're just finding a function, we say, oh, it's just the antiderivative. Essentially, you're doing the first part of this and not plugging in the a and the b. So I know I've gone a little ahead of where we are because you guys have asked me this question a few times. I feel like I owe you an answer. But here's the real, so here's what I just want to say for now, and then we'll kind of come back to this later. Definite integral. And you might want to write this down. The other stuff we'll come back to. You can look at it. The definite integral, you should think of as area under a curve. And it looks like the integral from a to b of some function dx, where you have to have limits of integration. And very importantly, your answer is a numerical value, right? When you find the definite integral, the answer is going to be a number like 5 or pi or negative 17.2. On the other side of things, what we've been doing so far are indefinite intervals. Also known as the antiderivative. Derivative of a function. It looks like the integral of f of x dx. There are no upper and lower limit of integration. And specifically, the answer is not a number. The answer is a function itself. And I'll lastly say here, remember the plus c. Over here, no plus c needed. So those are the main differences between a definite integral and an indefinite integral. And so what I say is the antiderivative of a function is essentially the same as an indefinite interval. But it's because of the nature of how a definite interval works and that we use its antiderivative to help us calculate the area under the curve. So there's this kind of whole machinery behind this, but that's the shortest answer I can give to your question there is. Hopefully that helps it make a little more sense. Yeah. But so for now, right, we haven't talked about area under curves at all. We have only been talking about just antiderivatives, and that's where we're going to be for a little while. I think we have at least a couple more sections to talk about before we really start talking about area under curves in earnest. So what I want to re-emphasize for all of you is that if you know some function is the derivative of something else, then you know how to find its antiderivative. So for example, you definitely know, even though you might have forgotten that you know, but you for sure know that, for example, the antiderivative of, I was going to pick something fun, but now, yeah, secant of x times tangent of x is equal to secant of x plus c. Because we know that the derivative of secant of x is secant of x times tangent of x. Then I'm getting a little ahead of myself though, because I think the next section is not the trig stuff, but it's the U substitution stuff. So yeah, let's go in that direction instead. So regular, powers of x, simplify first, get x out of the denominator. If it's in the denominator, right, bring it up to the numerator, change the sign of the power to the opposite of whatever it was. If it was positive, it's negative. If it's negative, it's positive. And then just use the anti-power rule. But then it's going to get more complicated. So let's look at something like this. Let's say I want to find the antiderivative of 5x to the 4th times x to the 5th plus 1. Do I want to square it? How much time have I got? I've got enough time, yeah. Squared. Okay. This is certainly not so heinous that we couldn't multiply it out. Now, if it was x to the 5th plus 1 to the 20th power, although technically one could multiply that out, it's got a lot of terms. You don't want to do that. And we're not going to do that. But let's multiply this one out first. So we're going to do this two different ways. The first way we're going to do is just going to multiply it out. So we're going to have, let's see, the integral of 5x to the 4th times, I got to FOIL this sucker out. So I got x to the 5th plus 1 times x to the 5th plus 1 dx, which is going to be the integral of 5x to the 4th times, let's see what I've got here, x to the 10th plus 2x to the 5th plus 1, which is going to be, let's see, 5x to the, the integral of 5x to the 14th plus 5 times 2 is 10x to the 9th plus 5x to the 4th. And now let's actually anti-differentiate it. We're going to get 5x to the 15th over 15 plus 10x to the 10th over 10 plus 5x to the 5th over 5 plus c. And we definitely should simplify these fractions. This reduces to x to the 15th over 3 plus x to the 10th plus x to the 5th plus a constant. Cool. Like, okay, big deal. So here's what we really care about with this. So the whole point of this example is that although you certainly could do it this first way, there's another way to do this. There's another way to really what we're doing, or about to be doing, is we're about to be undoing the chain, which is also known as U substitution. So here's the thing, we're gonna look at our integral and we're gonna decide that some piece in there, we're gonna set equal to U. And there's two criteria you're looking for when you're choosing what U should be. So here, we're gonna choose U equal to x to the 5th plus 1 for two reasons. Reason one, the derivative of x to the 5th plus 1 is also in your integral. So reason one, because u prime of x is 5x to the 4th, and 5x to the 4th is also in the integral. And then really, I've labeled it, all right, I've done that one first because it is the primary thing you're looking for. If you see a thing you can choose for u so that the derivative of that is also already in there, great. The other way we often look to determine what's a good candidate for u is a function that is stuck inside another function. So something that is maybe being squared, or you're taking sine of, or the square root of, or e to the power of, or what, right? Something that is essentially the argument of another function. So the second thing you look for is that u is quote unquote stuck inside another function. And in this problem, x to the 5th plus 1 fits the bill completely. It is both having its derivative also in there, and it is also stuck inside another function. So what I always think of when I think about a U substitution problem is it's a translation problem. You are translating from the language of your variable x to the language of your variable u, which means everything has to change. You can't have any x's left over when you're translating to u's. So everything that has an x in it has to become something with a u in it. And most importantly, the dx has to change to du. That is the number one thing you want to take care of. So let's look at how we're going to do this. Do I have enough room? Probably not. Yeah, I really don't. Sorry, always the worst when I don't have enough room. Key juncture here. So we're going to take our integral. You can still see that, yeah. So we're going to take our integral of 5x to the 4th times x to the 5th plus 1 squared dx. And we're going to be like, okay, u is equal to x to the 5th plus 1. And here's what I'm going to do first. I'm just going to take the derivative of that. So what's the derivative of x to the 5th plus 1?
4x or 5x to the 5th.
Right. Now, what's a way of writing the derivative of u? Well, I would say really, if I'm taking the derivative of u with respect to x, you're not wrong, but I'm going to write du dx. That's the more kind of official way. And the reason I'm writing it that way specifically is then I'm going to quote unquote multiply, although really we're just abusing notation here. I'm going to say that du equals 5x to the 4th times dx. And look, I've exactly got that. I've got 5x to the 4th times dx. So in my new integral, that's going to be exactly what is going to become my du. So I'm going to say again, when you're doing a u substitution, you want to make sure you take care of whatever has dx changing into du first. And then after that, deal with the rest. So then the rest of it is, oh, I have u squared. So I'm just going to write u squared. Okay, so now what's the antiderivative of u squared? Yeah, I'm just using the anti-power rule. So I'm going to get u to the third over 3 plus a constant. But then, well, I started off trying to find the antiderivative of a function of x. My answer should also be a function of x. So after you've done the anti-differentiation, then we're going to substitute back in what u is equal to. So this is actually going to equal x to the 5th plus 1 to the 3rd power, all divided by 3 plus c. So now the question I'm sure that's on all of your minds is, James, is that the same answer as what we got before? I mean, they don't look exactly the same. I guess I need to multiply this out to see if they're actually the same. So let's take a look. Fun trick, in case you didn't know it. Y'all ever heard of Pascal's triangle? There's this cool kind of trick for Pascal's triangle where I should use a newspaper. So like you start with a 1, and then 1, 1, and then 1, 2, 1, 1, 3, 3, 1, 1, 4, 6. And so on and so on. You keep going down, you keep adding these two things to get the next term there, like that. These numbers here give you the coefficient of if you multiply out like x plus y to a power. So for example, x plus y to the 0th is 1. And x plus, I know it's not exciting, x plus y to the first is 1x plus 1y. And x plus y squared is 1x squared plus 2xy plus 1y squared. And x plus y cubed is 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. And it goes on. You could say that x plus y to the 4th is 1x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the 4th. And go on. So if you ever have to multiply by something plus something to some power, you can use Pascal's triangle to figure out the coefficients really quickly. So back here, what that shows us, or what that allows us to figure out really quickly, is that x to the 5th plus 1 cubed is going to be 1 times x to the 5th cubed plus 3 times x to the 5th squared times 1 plus 3 times x to the 5th to the 1st times 1 squared plus 1 times 1 to the 3rd, all over 3 plus c, which is equal to x to the 15th over 3 plus 3x to the 10th over 3 plus 3x to the 5th over 3 plus 1/3 plus a constant, which if we simplify is x to the 15th over 3 plus x to the 10th plus x to the 5th plus 1/3 plus a constant. So let's double check. Are they the same? No, where'd they go? Where'd it go? Where'd it go? Okay. Are they the same? No. Are they close enough? Yes. As long as your answers differ by at most a constant, they are quote unquote the same as far as we're concerned. Because the idea here basically is really this constant here and this constant here are not necessarily the same constant. So yes, as far as I'm concerned, I have x to the 15th over 3 plus x to the 10th plus x to the 5th plus a constant. And down here I have x to the 15th over 3 plus x to the 10th plus x to the 5th plus a constant. So we're good to go. So sometimes, depending on your method of integration, you and someone else might get a different answer because you can end up getting a different, like differ up to a constant. But yes, this is good to go. We're fine. Question?
Yeah.
Okay, cool. So use substitution. The whole idea is to look for a good choice for you, and then to translate the problem into the language of you, and to differentiate and then translate back. Let's do, we got time for one more at least. Yeah. Okay. So the thing is, that one you can totally multiply out. But if you had something like this, the integral of 6x to the 5th times x to the 6th plus 2 to the 99th power, although technically possible to be multiplied out, not realistic. What happened to the plus 1 and the x to the 5th plus 1? Good question. Let's see. Let me see. You mean you mean right here? Is that what you're asking about? The one right there?
The one in red. Where you did the U sub. Yeah, that same paper.
Like here?
Yeah.
So from this step to this step?
Yeah.
So what we did from this step to step, and that's a good question. I wasn't very explicit. When we find what we're doing here is we're taking the derivative of u. So the derivative of u is equal to, well, the derivative of x to the fifth is 5x to the fourth, and the derivative of 1 is just 0 because the derivative of a constant is 0.
Okay, thank you.
You're welcome. Yeah, good question. Thank you for asking. So this problem, we hopefully can all recognize that the great best all the time choice for you here is going to be x to the 6 plus 2 for all the reasons. It's stuck inside another function and its derivative is totally there. So we're going to find the derivative. So we're going to find du dx equal to 6x to the fifth. So I'll point out there are at least 3 good ways of doing what I'm about to do. My personal preference is to try and isolate du. So I like to do it like this and say, oh, du equals 6, that's a 6. X to the fifth dx, and be like, oh, I've got that, great. Some people, though, prefer to do this. Some people like to isolate dx. Say, oh, well, I've got dx equal to du divided by 6x to the fifth. That way usually works just fine. Sometimes it can lead to weird things happening, but here it's totally going to work. So if I deal with this first, meaning I'm just going to replace dx with du over 6x to the fifth. Now, it is going to lead to my integral having u's and x's at the same time. That's okay as long as we eventually aren't there. So I'm going to write this as the integral of 6x to the fifth times x to the 6 plus 2 to the 99th power times du over 6x to the fifth. And the reason for writing that is because then I can cancel stuff. I can cancel this with that. And then I can replace the remaining x to the 6 plus 2 with, well, that's u. So you can say, oh, well, that's going to equal the integral of u to the 99th power du. But it is vital that your dx changes into du. Or if you prefer, and I do prefer, I would do it like this. I would rewrite this as, I might even move the 6x to the fifth over there. I would write it as x to the 6 plus 2 to the 99th power times 6x to the fifth dx. And that's like, oh, well, look, 6x to the fifth dx is my du. So that is just du. That's the way I like to see it. It's really the same. It's just, I don't know, different ways of actually thinking about things in your brain. And so then this here, after I've dealt with that first, right? Do this first, then deal with this. Oh, that's just you. The reason I keep emphasizing that is because occasionally there are problems where you plug in the thing that you said was u, but you actually needed that to take care of the du part. So it can be a little like, it can screw up your work if you don't do it in this order. So now we're going to have the integral of u to the 99th power du. Same thing either way, right? Either way, I'm getting to the integral of u to the 99th, or the antiderivative of u to the 99th. And then we're going to use the anti-power rule and get u to the 100th over 100 plus c. And then we're going to plug in what u is, and we're going to get x to the 6 plus 2 to the 100th power over 100 plus c. And that's our answer. We're done. And you can check the derivative, right? If you did the derivative of this, right, your function, if you want to write it out a little more in a way that's easier to differentiate, I would write this as 1 over 100 times x to the 6 plus 2 to the 100th power plus a constant. If I was differentiating that, the constant multiple of 1/100 stays out in front, and the derivative of some stuff to the 100th power is 100, those are going to cancel, times their stuff to the 99th, well, great, there's that, times the derivative of our stuff, which is 6x to the fifth. Oh, great, there's that. So we literally really are undoing the chain rule. We're trying to find the function that if you take its derivative and have to use the chain rule when you do it, you get back this. So really, if you're thinking about the chain rule, right? This, the thing that's your candidate for you is your stuff. And the other stuff you're hoping is in there is the derivative of your stuff. So whenever you're trying to do a U substitution problem, you should be looking for, oh, what's the stuff? What's the thing that I eventually had to take the derivative of and multiply by? That's your choice for you. We'll definitely talk more about this on Wednesday.